Welcome to Zero Knowledge, a podcast where we explore the latest in blockchain technology and the decentralized web. The show is hosted by me, Anna.
And me, Frederick. In this episode, Anna sits down with Rob from Parity Technologies to talk about his early work at Parity, how some of that has led into his work at Polkadot, and some of the exciting features he's discovered along the way.
Before we start, we want to say thank you to this week's sponsor, Trail of Bits. Trail of Bits is offering affordable packages for young technology companies who are serious about their security. It's often hard to hire security experts. It can be expensive, and tracking down the right talent could be time-intensive. Still, your team may have security questions right now, and the code you're committing may need that extra review. Trail of Bits has a service that can help. Crytic provides continuous assurance for your Ethereum smart contracts, making sure they're safe and functional. If you would like security help from this very experienced security team, integrated into every pull request during your development cycle, fill out the sign-up form on crytic.io. Now on to our episode with Rob Habermeier. So today I'm sitting with Rob Habermeier from Parity. Hey, Rob.
Ahoy.
How you doing?
Pretty good.
Now, this is not the first time that you're on the podcast, Rob. You've been on before, but this is the first time that I get to interview you, which is pretty cool. And today what we're going to talk about is a little bit of your background, how you started at Parity, the work you did there, your work on Polkadot, a little bit of an update around Polkadot and Substrate, and then hopefully we can get into some new ideas you've been discovering as you progress in this development. So why don't we start with where do you come from and how did you get here?
Okay. Well, I'm glad to be back. Now I can talk all about myself now. Yeah. So who am I and where do I come from?
Yeah.
So I'm Rob. I am I guess my official title is the co-founder of Polkadot. I come from the DC area. My background is, originally it was sort of computer security. That's what I was super interested in. I got into coding, game programming, optimization kind of stuff as well. And the security stuff is really what got me into crypto. But then, I was into this programming language called Rust, and that sort of the intersection of those two things is what brought me into the Ethereum world and in touch with the folks at Parity who are using both of those things. That was sort of my entrance into the crypto space.
What was the connection there between gaming and Rust? Because it's not a lot of games are written in Rust, so why would that kind of stuff have led you to Rust?
Oh, yeah, so that didn't lead me to Rust. The computer security stuff is... so I would do these things called CTFs, capture the flags. And the goal there is there's two kinds of CTFs. So one kind is where it's literal capture the flag and you're playing against other teams. And the goal is, everybody has a server and you're trying to attack each other's server and steal each other's flags. And the other kind is where you're just solving some challenges and every team has is trying to solve the same challenges. And that's where I learned how to do a lot of different kinds of exploits, like a return-oriented programming, smashing the stack, that kind of stuff that you can do when you exploit programmer errors that are dealing with low-level memory. And that's in 2013 or 2014. No, 2013, I stumbled on the Rust programming language, which said, hey, look, all of this stuff is not possible in Rust, and it's still just as fast as C++ or C. It was way different back then. It was super unstable. It was really early days. But as somebody who had actually, learned how to carry out some of those kinds of exploits, it really appealed to me. I was like, oh shit, I could actually, write something that's really fast. I like to write things that go fast, but I don't have to worry as much about things going wrong.
Cool.
Then I had this background of computer security, and I was super into cryptography and math. When I went to go study, I started to do a bachelor's in math rather than computer programming because I just thought that's more general. That teaches you how to solve problems. So that made it a really easy entrance into the crypto world over the course of 2015. When Ethereum was really starting to come up was when I ended up getting into the crypto world. It made it super smooth because I had all the background I needed in cryptography and math and programming.
What did Ethereum look like to you when you first stumbled on it?
Yeah, that's a good question. I think one thing that appeals to a lot of programmers in particular is the entire aspect of automation, where at some point you could just set things in motion and they just go, right? And to me, Ethereum looked like a great platform for setting up things that just run. Now, I think my perspective on that has changed quite a lot, because when you deploy things at that scale that affect so many people, it's never going to just run, right? There's always going to be some kind of intervention. But at the time, what really struck me was like, wow, you can just program anything, any kind of application to anybody all over the world can just jump in, and they don't have to, send their data over to Mark Zuckerberg or anything like that. So I thought that was really cool. And that's really what got me most into Ethereum.
You sort of mentioned that you were like into cryptography, but was that like a hobby thing? Was that something you were actually studying? I mean, we had Sean Bowe on some time ago, and his story is so interesting, where he like dropped out of high school to work with his friend who was a cryptographer. Like, he was just super into it. So I'm curious, like, how did you really get into that?
Oh no, I'm not that cool. So I was just
cool too. Different cool.
Well, thank you. Yeah, but I'm not that cool. So I was more of like a hobbyist cryptographer. It was like, oh, this is pretty neat. You can I was learning about all the programs. I got into Steganography, which is the process of hiding payloads within things like images, so that I could say like, hey Anna, check out this funny meme, and like, if the government is spying on us, they could see like, oh, he's just sending Anna a picture that's funny, like ignore that. But actually hidden inside the pixels, like I've slightly altered it so that it contains a secret message.
Wow.
So that kind of stuff. I got more into like an overarching view of cryptography and privacy and things like that. Understanding on a low enough level how this stuff worked, but I wasn't doing stuff like hacking on elliptic curve schemes or whatever Sean was doing.
So nowadays, though, you get a chance to work. You're working like pretty directly with researchers and like cryptographers a lot. Do you feel like, are you absorbing a lot from them now? Do you feel like your cryptography work or understanding is sort of like at an all-time high? Is this something you focus on now? Or is it more like is it more implementation?
Yeah, my approach has changed over the past couple of years. I'm very much interested in cryptography, and I think if I had no other projects or obligations, I would be like, one thing that I find really interesting is the zero knowledge stuff. Like I first learned about that at the Stanford Blockchain Conference in 2017. And I saw a presentation by Eli Ben Sasson about Starks. He was like, what do we call it? Do we call it Starks? And we did a show of hands, and he was like, okay, they're Starks. Cool. And after that, I was like, wow, this is so cool. I went up to talk to him. I was like, how do I actually get into learning that? And, from there, I went and studied up a bunch on elliptic curves and finite fields and, projective affine spaces, that kind of stuff. Brushed up on the number theory, and I got really into it. And I think I would be doing that at some point, but my main goal is to not get lost in details. I'm trying to accomplish something very specific with Polkadot, and my goal is to always know just enough about everything. I understand how public key cryptography works at a decently low level, but I'm not a cryptographer, right? But I can build protocols that construct crypto-economic incentives using that kind of knowledge. I like to have sort of a broad base of tools to draw on.
Cool.
Where you can build something more complex, more powerful out of all of it.
When you first joined Parity, though, you weren't working on Polkadot. You were working on something else. You were doing... What were you doing there?
Well, when I first joined Parity, Polkadot didn't exist. It was F-Core back then.
Parity didn't exist, exactly.
Yeah, exactly. Parity didn't. When I first joined Parity didn't exist. And the first things that I did were, one, I built warp sync for Parity Ethereum. So the ability, it's a very practical feature, but essentially the idea is to have the entire network of nodes periodically generate some snapshot of the entire state of the blockchain and then disseminate this via a BitTorrent-like mechanism to any new nodes who want to sync. At the time, it was really fast. You could get synced in like 30 seconds from the whole network. Now the Ethereum network is like 20 or 30 times larger, and it takes, a good time longer to actually get synced, even with Warp Sync. But it was, it was a nice introduction to the world of consensus algorithms in practice and synchronization securely.
So what you had done is actually you'd sped up the syncing process at the time by like a crazy amount, but now just because of the size of the chain, it's like, does the Warp Sync still help, or is it like too big for that to even be noticeable now?
Well, Warp Sync in principle is still viable, but it's going, like, this is what a lot of the Ethereum 1.x efforts are on, sort of to do further research into, I guess, adaptive warp and fast syncs. Like Geth's approach was fast sync, which is not to do a compressed snapshot of the state, but rather, you have this root of the state tree that's in every header, and just to download this recursively from your peers. So you download the whole state tree node by node, but it's way slower. You have to do tons of round trips. It's like, once you get one node in the tree, then you fetch its children, you fetch those children. So it's a lot of round trips. So the idea is, okay, what if we do something that's a hybrid of both, right? You have snapshots periodically, but you're downloading portions of the state tree as well that have updated since that snapshot. So you don't do snapshots quite as often, or you don't do snapshots that cover absolutely everything, but you do snapshots that cover most of the stuff, and then you sort of fill in the gaps adaptively. And it's much more difficult to do, but it can be done. So in principle, yeah, Warp Sync, stuff like that I think it's absolutely necessary for the challenges that Ethereum is currently facing, which is, what do you do when a blockchain gets heavy? Like, most of what you would put down on paper when you design protocols for blockchain is like, yeah, it's going to keep running. Like, people are going to be able to store all that information. But after a while, it does add up. And this is where you run into those very practical engineering problems. It's part of the divide between research and implementation that you see so much in this space, where the researchers will say, yeah, it can be done. And the engineers are like, well, I guess, right? But we have to write a lot of code to keep it running.
But even the engineers can't always predict. Like, I mean, I think you've probably had this really interesting front row seat to see a blockchain grow really big, kind of, even though I'm sure that people were working on predicting a lot of that stuff, like, to see it in action, all of these problems must emerge.
No, definitely. A lot of it is also that these engineering efforts involve oftentimes massive restructuring of large code bases. And you can identify what needs to be done, but the actual work to reorganize, to get things in a state where you can actually start to build out those new features, is also something that needs to be accounted for. So oftentimes it's not only that engineers won't see what needs to be done in the future, but they'll kick the can a little further down the road. It's like, oh, okay, we can postpone that a little bit, because it's just going to be such a monumental effort and resources. You need a lot of resources to do that. But, software projects don't scale just by adding more people onto them. It's like, there's only so many people you can have poking at one piece of code at a time before you're conflicting with too many people's work to actually be productive.
That reorg idea, like, we've talked a number of times on the podcast about like maintenance, but reorg is a different deal, because that's like recreate. You have to start kind of from the ground up and rebuild the entire thing, right? Oh yeah,
like you can run into kind of world shattering assumptions being broken,
Yeah.
I mean, not quite on that level, because you always are aware that these things sort of will happen, and you'll write your code sort of in a way where you can accommodate those kinds of changes. But then when you actually get to that point, you'll realize, well, it wasn't ready. That's one of the reasons we had a lot of lessons learned with Parity Ethereum, and we're still building it, but we've spent now a good 3 or 4 years just building Parity Ethereum, and we know what it takes to write a pretty robust blockchain client now, and we've taken a lot of those learnings into us with Substrate, where we can say, well, everything is really modular and flexible and pluggable, and that means that you don't make assumptions about okay, this is where the consensus engine is used, this is exactly where the network fits in. It's just you sort of let all the pieces control whatever parts of that infrastructure they need to.
We started with like what you worked on at Parity or ETH Core at the time in regards to Ethereum. But before I want to move on soon to Polkadot and Substrate. But before I do that, I am curious, what else have you worked on?
The main thing before Polkadot, I mean, this was while we were already planning out Polkadot, because we were investigating ideas like before stateless clients were named that, we were exploring things like stateless clients and different light client protocols, because we wanted to see what's the viability of putting light clients for other blockchains into a blockchain. So one of the things that I was researching and developing at Parity in the early days was a light client protocol. So just building that out from scratch over the course of 10 months, doing the research on like what's most efficient, designing the protocol and protocol messages. So it's a different protocol than what Geth uses, which is LES. What LES will give you is the ability to ask a peer many requests of the same type in one packet. So, if I want to get 20 different state tree nodes, I can ask one peer for all of them. And if they have all of them and they're honest, they'll return all of them. What I wanted to do with PIP was, minimize round trips. For things like light clients, latency is super important. Like if you talk about user interface, after you get past 100 milliseconds, things are really annoying. So I wanted to do pipelining in single packets, where basically I could say, give me the header with block number 1 million. Then from the state root in this header, prove to me the account with this address's balance and storage root, and then prove to me the storage at this key. So you could do all of that in one packet. You're doing all these like pipelining where you have unresolved outputs of prior requests being fed into further requests, but all within one round trip. And it can all be done super fast on the other side. You could even do smart contract calls and stuff. And that was really nice because it really minimized the network latency.
You just mentioned two acronyms, though. What was Geth's?
LES.
And what does that stand for?
Light Ethereum Subprotocol, I think.
And yours was PIP?
Yeah, PIP.
Which stands for?
It's the Parity Light Protocol.
Got it.
With the I in light is the I.
Okay, got it.
Because we know how to do acronyms.
Clearly. Cool. So I want to talk about Substrate, and I want to talk about Polkadot. One thing to note, though, is we do have an entire episode with Gavin that we recorded in November where he went into the detail of like the history of Polkadot and a lot of the core ideas. So I don't think we have to do that today necessarily. We don't have to cover all of it, but I think it would be good to reintroduce what it is, what those two things are, Substrate and Polkadot. But I think what I want to lead into after is like, how does light client work lead into that? How do they connect? Because I think there's kind of maybe some new insight I can glean from that.
I think I said earlier that Polkadot is a heterogeneous multi-chain system, right? So that's what it says on the tin. There is a lot more to it than that, and there's a lot of motivation behind it. I think it's a lot easier to start with the motivation briefly. I'm sure Gav went into a ton of detail in his episode. He's really good at explaining those kinds of things as well. So if you want a super deep dive on Polkadot, that's the thing to check out. But basically what it boils down to is the idea that right now blockchains, all the blockchain platforms that we've seen so far, or that we had seen at around 2016 or 2017, were all trying to do everything and be everything. That they wanted to be the bank, they wanted to be the platform for computation, they wanted to secure all the decentralized applications, and they wanted to do it all, on one single chain, that they were the layer one. And what we realized is that, for instance, with the smart contract paradigm, the way that you have to charge fees introduces some inefficiencies. So for instance, the gas metering, right? If I want to write an EVM smart contract, I'm breaking it down into bytecode. And that bytecode is little instructions like, okay, add a number, subtract a number, let's do some multiplication, let's write this to storage or read this, what's the author, those kind of pieces of bytecode. It's like really, really small granular instructions. And if you want to do something like build a DEX that has an order book, you're going to have to combine hundreds or thousands of these. Or imagine if you try to do some kind of elliptic curve cryptography verification, it's tons of math, right? And the way that gas works is that before every single one of these opcodes, you're stopping, charging a little fee. If they have enough to pay the fee, the gas cost, then you continue. So this is a huge inefficiency. You do tons of extra work whenever you try to compute something with smart contracts, but they're very, very general. You can kind of like write anything with smart contracts if you're willing to pay a fee. So what we realized with Polkadot is that you can rather, for specific purposes, why not build a specialized chain for that purpose, where you say, you don't have to do transactions in terms of these little opcodes, but you rather say, this is the transaction for making an order in the order book for a DEX, or for storing a file on a file exchange service, or for querying an Oracle on an Oracle service. And then you only have to pay a fee once. And that's vastly more efficient. Not to mention the fact that, for specialized services, you don't have to deal with fitting into the smart contract platform's representation of storage. You can make storage formats for the data that's kept on chain that is more efficient to the problem domain that you're trying to address. So this is one principle. Specialization is great for optimizing problems, but there's a caveat. When you specialize, you lose the flexibility to represent many different problems. You lose the network effect. If you have a smart contract system, all the smart contracts can talk to each other. So this is where a need for interoperability arises. You have a network of many chains which are specialized and very efficient for certain problem domains. One problem domain is smart contracts, because the problem that smart contracts are really good at solving is being general. And then you have the ability for all of these chains to communicate. And that's basically what Polkadot is.
I mean, I think that kind of contrast, the specialization, which could lead to, maybe faster times, more optimized computational capacity, versus this general approach, which would be you wouldn't have to fit into a certain box. You could do a lot more, but then you're going to be stuck with like long wait times. And as you mentioned before, kind of like this gas issue.
Yeah. Oh, it's pure engineering. Like, this is sort of a research versus practicality approach, because in research you would say, smart contracts can do every computation, but in practice we see that there's some constant factor there in their analysis that we can get down. We can make that lower. We can make things more efficient.
What I don't fully get though in the interoperability kind of explanation you just gave, though, is like, what would you be like creating different parts of a program somehow with these different chains? Like the example you gave before about the smart contract with like certain, opcodes, and like each one requiring a gas transaction. In this case, would you have entire chains dedicated to certain pieces of that? Like, would the chain only do something in a kind of program?
I think it's much more likely that chains will occupy key infrastructure positions. And the examples that I mentioned before of storing files, oracles, there's also stuff for like shielded transactions and fast transfers, plasma, things like that. Rather than pay gas costs for all the opcodes that it would take to represent those constructs, you can say, it's a linear overhead to make an order in the order book, so we're going to charge you a fee relative to the size of your order or something. I don't know exactly how that's an example that came out of nowhere, but in principle you get the idea, which is that you can levy fees once for things that would take levying fees many times in a smart contract system.
Got it. So you also have Substrate, which is connected to Polkadot but is separate from Polkadot. What's Substrate?
Yeah, so Polkadot is a very broad project. It says if there are specialized chains that fulfill some, constraints on how they are executed and how the blocks for them are produced, then we can connect them and we can build this network out of all of them. But of course, those chains still need to be built. And the tool for doing that we've made is called Substrate. Right. So the idea is it's like a blockchain toolkit, all those things that are actually pretty tricky to deal with in writing a blockchain node, like the database, sync, consensus, all of this stuff, the RPCs, everything except for what the blockchain is actually supposed to do, which is typically as a development team, building a new blockchain. That's actually what you care about, right? You don't want to get bogged down in like debugging some database issue or some consensus fault for ages and ages. You just want to make the blockchain's transactions do what you want it to do. And that's what Substrate is for. It's essentially to let people focus on the part of the blockchain that they want to build.
The purpose of Substrate is also to allow someone to create a blockchain that would be easily kind of implemented into the Polkadot system, right? Like it would have all the same, it's probably written in the same language. It's like easy to fit in, right?
So I wouldn't say that language is actually particularly important. In Polkadot, these blockchains that we connect are called parachains, and their execution is defined by WebAssembly code. WebAssembly is sort of like the thing that's been coming forever to kick JavaScript off the throne of the web. So it's actually a very portable, low-level bytecode, sort of like, what the EVM was aiming to be, but much more ubiquitous. And WebAssembly is targeted by many different languages. So you can write programs in Rust, C, C++, Go. Like there's many, many different languages, typically in the low-level spectrum that can compile to WebAssembly. So you technically could write a parachain in any of these languages. But Substrate, yes, to answer your question, without going off on a nitpicky tangent, is yes, it's made to plug well into Polkadot, but the projects are complementary. Like you can write something with Substrate that doesn't use Polkadot at all. And it would be nice, and we'd like it if you plugged your chain into Polkadot, but you don't have to. We sort of approach it in a couple different ways. So basically what it boils down to is Substrate is completely generic over its consensus engine. It doesn't make any assumptions about what is actually providing security for your chain. So, you can do your typical consensus implementations like proof of work. We have ones that we've invented called Aura, Babe, and Grandpa. We have implementations for all of those. You could do a Tendermint implementation for Substrate. But there's also one other consensus engine we've implemented for Substrate, which is what we call Polkadot Piggyback Consensus. And that's the idea that you can write a chain in Substrate that draws its security from the consensus of another chain. Right, so it's just piggybacked onto it, and that means that it's it's not its own sovereign chain, and that's how you would create a Substrate chain that deploys onto Polkadot. The other thing that we've done with, while we're on the topic of pluggable consensus, is we've set things up. We haven't implemented this code yet, but it's a feature that's on the roadmap for Substrate, is the idea of swappable consensus, hot swappable consensus. It's the idea that not only can you choose what consensus engine you deploy your chain with, but while the chain is running, you can change the consensus engine mid-flight.
Whoa. What would that be used for? That's wild.
So one of the things that we've done when designing Substrate is really try to put as much flexibility in the hands of project developers as possible. And that means that there's no platform lock-in from Polkadot, for instance. That means that if you want to be a parachain, you don't have to be a parachain forever. Or if you start as a sovereign chain, one that provides its own security, you don't have to stay a sovereign chain forever. So that's sort of the goal of swappable consensus. You can start as a sovereign chain. Imagine this is the life cycle of a parachain, right? So the chain is launched. It has its own validator set, its own security, and it's providing a service on its own. But it's not part of the Polkadot network. But then some people from the project decide to buy a parachain slot in the open auction when one comes up, and they get a parachain slot for 6 months or 12 months. After that point, they can trigger a swap of consensus to the Polkadot piggyback consensus engine so that their chain, which was previously sovereign, will become a parachain. It's technically a hard fork, but it's a hard fork that you don't need to distribute a new version of a client for. Like that's typically what happens with a hard fork, is that you have to say, okay, everybody update. You got to update before this day. If you don't do it, you're just going to be off on your own chain, and that's useless. You're useless. Update, right? We're doing something completely different, which is that with swappable consensus, your Substrate client will just support a bunch of different kinds of hard forks that it can do, and everybody's clients knows how to do these consensus hard forks, at least to the consensus engines it supports. So you won't need anybody to update their client specifically for this hard fork. So they'll hard fork, become a parachain, live as a parachain for a while. Maybe after a couple of years, they'll decide we don't want to be a parachain anymore. And then they can swap back to sovereign consensus of some kind and cease to be a parachain.
Could you use this also? When you said swappable consensus, though, I thought you could switch between proof of work and proof of stake or something just for fun.
Oh, absolutely.
Without it necessarily interacting with Polkadot.
Yep.
So but you also said mid-flight. Is that sort of mid, while the blockchain's live?
Yeah, post-launch.
Okay.
Yeah. No, absolutely. You don't have to use this in a way that's connected to Polkadot at all. The framework that we've built is for navigating between arbitrary consensus engines. what we've designed. We haven't coded it yet. That's planned for, a later version of Substrate, but this is the roadmap for Substrate. And, that is how it fits into our vision with Polkadot. The idea, for instance, that parachain developers can deploy their parachain before Polkadot mainnet is even launched, right? So they don't have to wait for Polkadot mainnet to be launched to actually start delivering their product. And then when Polkadot mainnet is launched, they can attach to it.
Cool.
Right?
Is this done by so you sort of mentioned the clients don't have to update, but does that mean that there's an auto update pushed? Is it sort of like...
It's sort of like your client is pre-ready for certain types of hard forks. Now imagine if I want to swap from Consensus Engine A to Consensus Engine Z, but Consensus Engine Z was sort of newly introduced, then you would kind of have to wait for people to update their Substrate versions, right? Or their, that node written in Substrate version. But imagine if Consensus Engine Z has been part of the Substrate catalog of consensus engines for a good while. Or the project developers want to develop their own consensus engine X. They think, okay, at some point we're going to want to fork to this consensus engine, but we don't know when. Then they can disseminate a client update that contains consensus engine X. And after that point, they can do the hard fork whenever they want. So it's not like they have to do an emergency update. We're going to hard fork right now. It's just they can plan ahead for it. And if Substrate has a large suite of consensus engines, that means that blockchains are going to support these kinds of hard forks across almost every client of every blockchain.
When you're implementing with Substrate, are you basically will you be having a sort of a large selection of consensus mechanisms that are already kind of written into the client itself? And then you can choose which ones you use depending on certain things, and then and that would already be in the client itself, so it wouldn't be about downloading a new version, but rather triggering a new version, or I'm a bit unclear on the difference between a downloading of a new client and updating of this thing.
So downloading and updating are basically the same thing in this case. You would have to update, right? But the fact that these consensus engines are sort of pre-bundled, or that they are just part of the standard Substrate suite of consensus engines, or that developers might have the foresight to include them well before the fact, means that at the time that you actually decide to trigger the switch, basically everybody has already updated. You don't have this situation where it's like, okay, emergency update time, we're going to do a hard fork. You can just sort of decide at the drop of a hat, via any process whatsoever, let's change the consensus engine. You don't have to do, anything formally to say, okay, but then it's going to be a big drag because we have to distribute this client update. You can just say, issue some kind of signal in the chain via, a governance system or something like that says, okay, switch. And at that block, it'll just switch.
Wow.
For anybody who's updated their client in the last 6 months.
Oh,
right?
Cool. As long as the consensus mechanism has been included in the bundle.
Yeah, exactly.
Got it.
Yeah.
And that's sort of what you were saying there, where it's if there's a new consensus mechanism that isn't included, it would first have to be included in a Substrate bundle and then downloaded and then...
it doesn't necessarily have to be part of the suite of consensus engines that's included with Substrate itself. It could be the client developers of some project would say, we have our special consensus engine, and now that we've developed that, we're going to include it in all of our releases from this point on, and then at some point we're just going to trigger the switch.
Cool.
Right.
I have a question. How does this, going back to your background with light clients, you sort of mentioned that before Polkadot, you guys were already experimenting with these light clients.
Yeah.
How does that actually relate? Is there a connection between the light client work and what Polkadot is? Or what Substrate is?
Yes, I think there's a huge amount of that. In particular, the stateless client concept. So now Alexei Akunov has sort of taken over that mantle for ETH1X. So he's released a really nice blog post with up-to-date statistics. But at the time when I was doing this towards the end of 2016, I also had my own graphs and things. So the statistics that we were collecting on the Ethereum blockchain, which was the best sample that we had at the moment of a blockchain that's actually doing significant computational work, was to see how big the state proofs were when you wanted to execute an entire block. So that is, if I want to execute the block we have this whole state tree that contains, all the accounts and smart contract data. It's a tree of nodes. What if we just packaged up all the nodes that you need to execute that entire block? How big is that package, right? And we found that for the Ethereum chain, typically at that time, it was in the range of a few hundred kilobytes, but we could see that there was a trend going up because the state tree does get bigger. And as it gets bigger, it gets more inefficient too, because it gets lower, it gets deeper, right? It gets deeper. The more nodes that you add.
Is it sort of like more leaves on the Merkle tree? Is that what it is? Or is it more entries in a...
It's not just about leaves, but it's about how many accesses you have to do. It's like how many children do you have to traverse?
Okay.
That's what I mean by it getting more inefficient. There's like, if you have a tree with one item, then lookup is always just, the one node.
Yeah.
Right. But if you have to go 4 levels deep or 5 levels deep or 6 levels deep, you have to go, more, you have to do more for every piece of state that you want to read. And that makes the proofs more inefficient. So even though, the amount of pieces that you might read for a given block would stay the same, for a given transaction per gas, let's say, would stay the same, it gets more inefficient. Those proofs get bigger because you have to punch through all those levels because the entire state tree is much bigger. And this is all cryptographically proven because these state trees are Merkle trees, right? That's the state root in the Ethereum block header. But this is essentially how Polkadot works. Polkadot is a system of stateless clients. The validators of Polkadot who are signing off on whether parachain blocks are good or bad, those validators are shuffled between parachains. So if you have 10 parachains, I, as a validator, from block to block, might get shuffled from parachain 1 to parachain 5 to 3 to 7, over the course of just a few minutes even. And that means that I, as a validator, don't have time or space to keep around the entire state of every single parachain. We have nodes who are living on a single parachain called collators. Those store the entire state of their parachain, and they generate these stateless client proofs of execution for new blocks to send to validators. Validators check those, ensure that the proofs remain available, and then sign off on them. So the stateless client research was really pivotal in finding out whether the idea of Polkadot was going to be viable. I remember in 2016, I had a hacked version of the Parity Ethereum client that was just going through every single block in the chain and seeing how big is that proof. And we looked at the graphs, like there was this whole spurious dragon state bloat attack, and those were out of the ordinary. There was like 30 to 50 megabytes typically, but mostly they were on the order of a few hundred kilobytes. And that's where we saw, okay, for a blockchain that's seeing as much throughput as Ethereum, and with the current state of internet infrastructure, this is actually doable. And this is an architecture worth pursuing.
The collators you just mentioned, are they almost like archive nodes today? Like you're saying they have the full state. Are they like a regular node? Are they like because the full state, like the state changes every block?
Every block.
So therefore, I mean, we kind of mentioned this on a previous podcast where if you really want to see the history of the state, you'd actually have to create snapshots at every block to see that and look back. And
that's an archive node.
That's an archive node. Are the collators related? Or are they more just like holding a regular node?
Collators are what we would call full nodes.
Okay, yeah.
They store when I say the entire state, I meant the entire state of the head of the chain.
Okay.
But that's a shorthand, because what I really mean, because the consensus is not instant finality, and you can have safety failures where you might have forks even if it's instant finality. What I really mean is the collator nodes keep state for all viable heads of the chain. So what anybody might reasonably perceive to be the head of the chain. So that's usually, across a few different short forks and back maybe 100 or 1,000 blocks. That's about how much state a typical full node would keep in the Ethereum network as well. That allows you to account for reorganizations and things. But when I say collators have the full state, they have the full state of the block that they are building on. Whereas validators have absolutely nothing, right? They have nothing. They are light clients of every parachain at once. Got it.
So you just mentioned two sort of actors within Polkadot, the validator and the collator. Mm-hmm. Originally in the paper, there was like fishermen and nominators. Yeah. So has that changed a little bit? I know even when we interviewed Gav back in November, he had sort of talked about how there might be sort of cross action, or like you'd be doing two actors' jobs at the same time.
Definitely.
So where's it at now?
Yeah, well, I think the like the 4 roles that we came up with are convenient for economic analysis. But in practice, you would be doing more than one at a time, simply because when you're performing one role, you may be well positioned to perform another. So in particular, you mentioned nominators and fishermen. I think of these two, fishermen are more interesting. So I'll mention what nominators are briefly, but essentially they are people who vouch for stakers who are validating, right? So validators stake their own coins or their own dots to validate, and nominators say, I trust that guy. I want to get a portion of his rewards. I'm going to back him. But if he gets slashed, I'm also going to take a hit.
So aren't they just, I mean, nominators to me sound a lot like delegators in other systems that just recently we had actually a few episodes on proof of stake and validator setups. Can I, at least, or can our listeners for this purpose just like combine those two as a nominator or delegator?
Yeah,
are they different in some way?
I think it's like at a very high level, they're similar. But typically DPoS does not propagate slashing onto the delegators.
I see.
Which is what we do. And the other thing is we use an algorithm called partial fragments method. It takes a voting algorithm from the 1800s that's very applicable to this use case as it happens, to basically have nominators say which candidates they'd be willing to support, and the system will automatically apportion their stake across those different candidates. Their nominated cool. stake, yeah. This is not how DPoS typically works.
From the systems that I've seen so far, there are delegation tools like coming out, and there's some talk of like other maybe wallets offering this kind of stuff, but it doesn't sound like in any way that it's automated or within the chain itself. These are often external pieces of software that you'd be running in order to delegate
so
to
the fragments method takes into account not just your own preferences, but everybody else's preferences. And this is not something that's possible to do just by adding on an extra layer, right, of delegator tools. Anyway, so that's nominators. But then we have fishermen. So what fishermen do is they're looking for misbehavior. They want to see who fucked up. So earlier on, I said validators are getting state proofs that they can check parachain execution with, and they make it available, and they vouch for it. So the reason that they make it available is that then fishermen can download that proof of a block's validity and check it. And if it turns out to be bad, then they can basically file dispute, and any validators who signed off on that block being good when it has now been proven bad by a fisherman will get slashed. And the fisherman will get a portion of that stake, right? They have an incentive for doing something here. They get rewarded. The hairier question is always, what do we do if the validators say it was available but it's not? Like, for instance, with a block validity proof that never existed because the block wasn't valid. So then we have availability games where fishermen, if they can't seem to find the data to check whether a block was good or bad from a parachain, they query. They ask around, and if they can't recover it, we have a whole economic game around this. Then they'll issue another kind of dispute, which leads to the offending validators being slashed as well. But it becomes more subjective at that point.
This is all automated. This is very much just like, I imagine it's built into the software. Like you would, if you were a fisherman running fisherman software, you just basically, it would all be automatically happening for you. And so the only way a validator would ever actually do something incorrect would be like if it went offline or if it had injected the wrong code or something like that, right?
Well, in general, if they would use the client software provided by honest developers, they would not misbehave except in the case of bugs. Mm-hmm. But we're dealing with adversarial BFT systems here, where we're assuming up to 1/3 of the validators are malicious and collusive
and running alternative software.
So we don't care what software they run. We're just worried about like what are they signing and sending over the network, right? They're running arbitrary evil software, right? in practice, that's going to be hacks of the official clients, official as those official clients get. We for the purposes of security analysis, we don't really worry about what software exactly they're running. We worry more about like what people do within a protocol. And we are considering up to 1/3 of validators being malicious, right? But we've got a system where validators are split into groups and randomly shuffled across chains. So even if the whole set of validators is only 1/3 malicious, you could very easily get a parachain group that's majority dishonest, right? And that's a problem because if your threshold for inclusion of a parachain candidate is 51% of the validators within that group signed off on it, then that can be easily compromised by that kind of case where you have that many malicious validators in the system overall. So what we do is we try to set up a system where it's very hard to finalize blocks where data isn't available. And if you have one fisherman for every parachain and data is available, you can always find out who lied. And we also set it up so that even if a block is finalized or authored where data wasn't available, but you have some constant number of fishermen querying availability overall, then you can always prove who failed to make data available, or rather that the data is not available.
So I want to move on from the actors because I kind of want to talk about the general setup. We've sort of mentioned this: parachains, different chains, interoperability, connecting them. As I've understood it, there's like a overarching relay chain. There's something that's like the security. It's where the consensus is happening, and the parachains connect to that, and they get to share that security. All of these actors you're talking about exist in the relay chain, right?
Well, the collators are sort of half and half.
Okay.
Collators are, their home is one parachain.
Got it.
And fishermen likely too. Fishermen may also be more likely to catch out bad parachain blocks because they're watching a specific parachain.
I see.
Right? And collators, being on a specific parachain, are well equipped to be fishermen.
Okay, so would you say that it's often going to be like a collator fisherman as the same actor?
Very likely, yeah. I'm not saying that you have to be a collator to be a fisherman, but if you're already running a collator and you've got a key set up that's signing things and making you money in the background, you might as well have it fish for misbehavior.
Now let's talk a little bit about like these comparable solutions. So recently I had Sunny from Cosmos on, and we talked about the Cosmos model, which is also an interoperability protocol. And it's also about like connecting different chains instead of having the single chain that's a generalist or smart contract chain, having different sub or other chains connected. What we talked about was this idea that like certain chains would require different security. So, for example, something like a chain for CryptoKitties wouldn't need the same security as a chain that was for a stable coin or something like this. In the case of Polkadot, all of the security exists in the relay chain. So this would be a consistent security model, despite maybe some chains not needing so much security. So I'm just curious, is that overkill? Like, do you need the same security on those two chains?
Well, one thing that's kind of hard to tell a lot of the time is how much security you're going to need in the future. I mean, imagine like very early stage CryptoKitties, nobody would have really put much security on it. But once it really took off, it needed a lot of security because those kitties became pretty valuable. And it's actually very possible to 51% attack and make some money there, right? Imagine if it was secured by a very weak chain. This is sort of the problem with like the bridging approach. So, for instance, if you have many different chains which are all just bridged to each other, and let's say you have chains A, B, and C, and A is the weakest, and you have an asset coming from A bridged onto B and then bridged further from B onto C, but then A is weak and it's 51% attacked. Then those tokens that you think you have on parachain B are actually garbage. So it's not even just that you can like cut off connections directly to weak chains if you're worried about like garbage tokens that could be 51% attacked and pulled out from under you, but you have to disallow all transitive connections too. So that approach has some real problems because one thing that it does is sort of hurt the idea of economic abstraction. So economic abstraction being the idea that you can treat all tokens equally in terms of they will all follow the interface of token, which is that you can transfer, you can receive, you can approve, someone else to make some transactions on your behalf, things like that. Now, if you use this bridged model, you have to do basically due diligence on, imagine if you were trying to build multi-collateral DAI, it wouldn't work because you have to do due diligence on every token that's going to be collateralized. It's putting a lot of unnecessary burden on the user that's actually not going to be carried out correctly. And I think that's a real, it's not the right way to approach the problem of different chains are going to need different security, which I do agree actually is the case. So the way that this fits into specifically the different chains need different security, the way that this fits into our roadmap is the idea that Polkadot 2.0 will have hierarchical relay chains. So you have a relay chain at the top. That's the Polkadot we've talked about right now. You have a relay chain with parachains attached to it. And all of those parachains have the same level of security. The security is split evenly across all of those parachains. But what if one of those parachains was itself a relay chain, right? Then that parachain is taking the security it has from the top level relay chain and splitting it amongst its parachains. So that's how you solve the problem of some chains will need less security than others in the Polkadot hierarchy. You just push it further down the tree of chains. And it's going to take a bit longer for messages to propagate all the way up that path to the root of the tree and down some other branch of the tree. That's the price you pay for having less security. You're less prioritized, you're less important, but you're still protected against being 51% attacked because you can't be 51% attacked with all the other chains in your group being 51% attacked.
So if there's something connected to the sub-relay chain in this model, what you just sort of said, would it take more time for things to be secured? Or what you sort of mentioned, it would take longer. It would take longer to go up and down the thing. So is that sort of you have the same amount of security, but it's slower? Or you have less security?
So there's a couple different things that are getting mixed here, and I'll address them one by one. So one, it will have less security simply because it is easier to 51% or 34% attack the entire validator set of that sub-relay chain because they are simply not going to be as highly staked as the top-level relay chain, right? So it is possible to do bad things on that relay chain. That's one thing. So it is less secure. And that's why I say the solution to the problem of some chains won't need as much security as others is to push them further down the tree of relay chains. Now, the other thing that was questioned was, does that mean that the blocks will take longer to be produced or finalized? So they'll be produced just as fast, but they will be slightly longer to finality because finality flows from the root of the top level relay chain, which means, let's say we have top level relay chain, you have a relay chain below it, and then you have parachain A connected to it. So you have to submit a block for parachain A. It's included in the lower level relay chains block. Then that lower level relay chains block is included in the top level relay chains block. Then when that's finalized, but you have to go through this extra step, right? Before it's finally somehow referenced by hash in the top level relay chain. That's what it takes before it can be finalized.
Those blockchains that require less security, could they still go at the same speed or even faster?
Sure. They can go faster. It's just that they have a slightly longer latency to finality.
And that's where sort of the less security comes in. It's possible that for a period of time, a false block is there and then would need to be fixed.
Well, it's even more so than that. It's that the entire parachain there can be adversarially overwhelmed just because that lower level relay chain, we're assuming the adversary has 33% of all dots, right? So that lower level relay chain isn't going to have a one-to-one correspondence in stake between the top level relay chain and the lower level one. So the adversary that owns 33% of all dots can easily 34% attack that lower level relay chain. Right. And that's where you can cause problems by, attacking all the parachains on that lower level relay chain at once.
I have one last question on this, which is why would you create these chains with less security in the first place? You sort of mentioned they can be fast or the same speed, they will have less security. But is it like, yeah, I don't understand why wouldn't you want all chains to have the same security?
Well, it's just more that different chains are going to experience different levels of demand and use, right? That's economics. Some of them are simply just going to be more broadly applicable and have a bigger market than others. So that means that if you split security perfectly evenly between all chains, it's not just that you're choosing to give more security to other chains. It's that you're also taking away a bit of security that, some other chains might deserve a bit more. So that's kind of the nice thing about the hierarchicality approach, is that, your chain, depending on how much security it needs, can slot itself in somewhere further away from the root of the tree of chains.
So one other thing about that I'm aware of about like Polkadot is that you have to, I don't know if the word would be stake. You have to lock dots in order to like rent out a parachain slot.
That's right. Yeah.
In this model, do you imagine like more parachain slots, or is it like cheaper parachain slots?
Yeah, they would be way cheaper.
Okay.
Because there's less demand for them. Like the highest most. So the one thing that I didn't get to in the previous explanation is that it means that you'll have higher latency for message passing when you have a chain that's lower down in the tree of chains. Because when I want to send a message to another parachain and I'm in like a sub chain, right? I have to send it to my relay chain, the relay chain above that, the relay chain above that. And then if I'm going down into another part of the hierarchy, I have to go down, down, down. And then eventually I will get my message over to the parachain that's in like, another branch of the tree of chains. But when you are closer to the root, that means that you always have less distance to travel for your messages.
And so this is sort of a premium place to be.
It's a good place to be for very heavily trafficked pieces of infrastructure.
And maybe parachains that have high value.
Yeah. What you could also imagine is that, on every relay chain, you might have one or two different smart contract instances, like, an Ethereum-like or something like Edgeware, where you have WebAssembly smart contracts. And having a smart contract live on the smart contract chain that's at the very top is going to be way harder too. And the gas fees are going to be more expensive because it's way more trafficked. But you're going to be able to send messages from your smart contract that reach every other parachain fairly efficiently.
Cool.
Yeah.
So what I'm kind of curious about, like going back to your background, I'm kind of happy that we started this episode looking at like how you started and the stuff that you were trying out and the different pieces of the Ethereum client you were working on, and how that kind of led you to develop a lot of skills or insights into how to do Polkadot stuff. Now, what I'm really curious about, you've been working on this project for how long?
Almost 3 years. We started in late June 2016. It's now mid-June 2019.
Are there any new ideas that you've picked up as you're kind of building this out?
One thing we've been thinking about a bunch lately, as we're moving further and further on with our iterations and getting closer and closer to what we originally wanted to ship, which was basically an ability to get security for a bunch of different chains and pass messages between them. So the next question that follows logically after that is, how do we know that what we get out of those messages is actually good? And that's actually a super tough question to answer, because you could have a parachain with its own governance, right, where it can actually change what its code does. And you might know that, okay, at the current time, when I'm building my application, I know that messages that come from this parachain that say, I burned some of this token, please mint some correspondingly on this side, or anything like that, where a parachain says, I've done something. How do you trust that when those parachains might be able to change their code arbitrarily, or if you want to deal with new parachains that didn't exist at the time when you deployed your app, right? You can't account for all future possibilities. So this is where we've come up with a new concept. It was originally put forward actually by a user on Reddit, and he framed it as smart protocols. And we've taken it and refined it a bunch, and we're calling it trust wormholes now. But the basic idea is that for those things where you need to guarantee that a parachain actually has accountably done something, you don't rely only on the parachain's code to do that, but rather you can create something sort of like a smart contract, sort of like it's a trusted piece of code that any parachain shares, and it controls a piece of state on that parachain. So, it might be for tokens. For the token abstraction, it could be a piece of accounting for all tokens that live on that parachain. So then when I want to transfer a token from parachain A to parachain B, parachain A actually tells the trust wormhole for parachain A, transfer the tokens from the trust wormhole of parachain A to the trust wormhole of parachain B. And the trust wormhole can actually be trusted because its WebAssembly code is registered on the relay chain and it can't be subverted by any parachain's governance. So that means that the trust wormhole, when it gets the command to transfer some tokens, will actually burn the tokens. And it will send a message that goes over to the trust wormhole of parachain B that says, I have burned the tokens. And parachain B will be able to recognize this as actually having had happened.
And then would you take that, how does that then go out of the trust wormhole into the parachain?
So trust wormholes can talk to each other and they can talk to their host parachain.
But nothing else. The trust wormhole of parachain B cannot speak directly to parachain A.
That's correct.
Okay.
But the trust wormhole from parachain B can tell parachain B, hey, I've received some tokens. And this is sort of our way around that leaky abstraction thing that you get when you bridge a bunch of chains together, where it's the chain that's the lowest security becomes the weakest link. This way, even if chains are changing the way that they operate out from under you, they can't pull the rug from under your feet. They can't make your code accidentally accept a double spend. And it doesn't apply just to tokens, but tokens are just a premier example of this. But it sort of applies to all interfaces where you are expecting that some kind of accounting or execution has been done prior to an event being emitted. So that's the generalization. So the way that you apply that to tokens is the accounting or execution before the event being emitted is that the tokens were actually burned before an event that says I burned the tokens.
But it could be any event.
But it could be any event. Yeah. It could be like I have done the work, and then it will send a message that says I did the work, and then somebody gets paid right on another parachain.
Could you, in these cases, run something within the trusted wormhole on one parachain and send the results to the second one, kind of like doing off-chain computation? Or is it only for a change in state or a message or something like this?
Well, you can make the trust wormhole run as much execution as you want, but it's always going to be on-chain computation. So these do trusted on-chain computation and not any kind of off-chain work. So it's always going to be part of the state transition of a parachain.
Okay.
Alongside the transaction execution.
Something about this seems a little similar to TEs or trusted execution environments, but it's not exactly the same because it's not in the hardware necessarily, right? This is where is this? Where does it exist?
I think that it's a very good analogy. So one analogy we've used to talk about Polkadot and parachains is that parachains are like computers and Polkadot is like the internet.
Okay.
Right? And if you think about, okay, how do I get trusted messages from a computer to another computer over the internet? TEEs are one approach to that because you have this trusted enclave that's actually signing things, right? So this is sort of the same principle applied to Polkadot. How do I get a trusted message from one parachain to another over Polkadot? Through a trust wormhole. And the actual one acronym we probably will end up calling it this, but trust wormhole sounds kind of cooler, but we're thinking of calling it SPREE, which is Shared Protected Runtime Execution Enclaves, which is an homage to trusted execution environments.
And an homage to the river that runs through Berlin.
That's right. That's right. Although we would say Spree then.
Yeah. But I'm sure that's where it comes from, right?
Yes, yeah, that's definitely where it comes from.
Okay.
Yeah. So we're really good at acronyms at Polkadot. We've got BABE, which is our consensus algorithm for the new blocks, which is called Blind Assignment Blockchain Extension. We've got Grandpa, which is for the old blocks, which is Ghost-Based Recursive Ancestor Deriving Prefix Agreement. And now we've got Spree.
Very nice. One last question about Spree or these trusted wormholes. How are they different from TEs? So you've made the comparison of how they're similar, but they're not really exactly the same. And also TEs have all these like issues. So
the nice thing about Spree is that it's actually going to work, unlike TEs. But like they're like TEs, but if they did work and you mapped it onto Polkadot, the main reason being that TEs draw their trustworthiness from trusted hardware, which attackers have clearly been able to break without too much effort, via timing attacks or just bad cryptography or all kinds of weird CPU tricks and meddling. But with Polkadot Spree, we're not really getting into anything that crazy. It's just making sure that deterministic WebAssembly code that's registered on the relay chain for everybody to see, that has been agreed upon by consensus, to make sure that it's been run correctly. And that's not a particularly difficult thing to do because it's all deterministic. It's not as hard of a problem as building TEs.
And it also sounds like it's all like this will be open source. It'll be it's code. It's not you're trusting in a chip manufacturer.
I guess the parallel would be a Spree module, a trust wormhole, which had a bug. So, one for accounting and tokens, since that's the example I've used already, might have a bug where you can force it to send the I have burned the tokens message when it didn't actually burn the tokens. But these are going to be very likely open source modules. They're going to have to be very well audited before the governance would allow it to end up anywhere on the relay chain. And since they are intended to be the underpinnings of secure interchain communication, they will have to be very well checked.
And will be eventually open source, and then everybody
of
can
course.
see it anyway.
It's not something that necessarily even the Polkadot devs are going to write, right? It's a general construct where anybody can put forward a trust wormhole.
Cool.
For instance, you can have trust wormholes that run smart contracts, and then you can give every parachain a little smart contract component as an idea.
Nice. Is this a wish out into the world?
Just a little idea.
Cool. Well, listen, Rob, I want to say a big thank you for coming back on the podcast, and this time speaking with me.
It's great to be back.
One day you'll speak to both me and Frederick.
Yeah. So I remembered when I actually was on the podcast last time. I think it was like February 2018. So right in the beginning.
You were also in Italy.
Oh, that's right.
Oh, that's so weird, actually.
The 2 times I've been to Italy in the last 2 years. Okay.
You've ended up on the Zero Knowledge podcast.
Yeah, chatting to one of the hosts at the time.
Well, anyway, thanks again for being on, and I hope to have you back on soon. And I sort of put this towards, I asked Sunny this, and I'm going to ask this to you as well. I would love to have you come back on sometime and actually do a deep dive comparison between the two protocols, because I feel like there's a lot to get into.
Yeah, I'm excited to see what kind of commonalities can come out. One thing that the Cosmos team has done a lot of work into is, for instance, how these kinds of cross-chain communication are going to work. And it's interesting to see if those same kind of protocols can be adapted onto Polkadot, and we'll end up with a much larger interchain ecosystem encompassing both projects.
Cool. All right. Well, then, thanks again for being here.
Yeah.
And to our listeners, thanks for listening.